Okay, good afternoon. Thanks for coming to my session. This is Sanhong from Alibaba. In my session, I just would like to share some work we are working on OpenJDK. Here's the agenda. The first part, I think I would introduce overview about how Java has been used at Alibaba. I think this is the introduction. The major part is I just want to go through the three major features we developed based on OpenJDK. The first feature is we called elastic heap, and the second is Java-warmup. The last part I just go through. We already do some extension for Java flat recorder, and I just want to share some reason and motivation behind why we want to do extension for JFR. Okay, let's go start. Okay, this is a picture about Alibaba infrastructure. You can just look at this picture from the bottom to up. And Alibaba already has our own data center across the world. So on top of that, we already, in system software layer, actually we customized the Linux. We also customized the OpenJDK for our needs. And yes, we also have our own resource scheduling system, actually, which is based on Kubernetes ecosystem. And yeah, we also have our own database, ocean-based and PolarDB. And on top of that, we have different workloads. And you know, we have workloads for e-commerce, for financial, for logistics, and also for Ali Cloud. So lots of things. This is a show about the Java usage in Alibaba. Actually, we built our software based on broad open source ecosystem in Java. You can see we already used Jetty, Netty, and Tomcat, Elasticsearch. For big data, we also have Spark, Flink, and so on. So we use Java at a very, very massive scale. Actually, you can see, look at this number. We have millions of instances of JVM, then with about billions of lines of code. This is the major focus in my session for this talk. We have our own in-house OpenJDK implementation. We called AJDK internally. Based on OpenJDK, you can look at this picture on your right-hand side. We already developed a couple of features. For example, multi-tenant. By using multi-tenant, which allows you run multiple applications into the same JVM instance safely, we just provide resource management for each of them. We also implement Wisp. Wisp is you know, very similar to Loom. Loom is an OpenJDK project which implement you know, implement light thread. You know, just do scheduling at a user level. And you can write code in synchronous, but you can get performance as asynchronous. In March of this year, we open source Alibaba JDK as Alibaba Dragonwell. You can look at the picture on your right hand. Some features has been included in Alibaba Dragonwell. JFR, Java-warmup, elastic heap. So for long term, actually, we are planning to ship all of them to Alibaba Dragonwell. Also, importantly, we also would like to talk with OpenJDK community for contribution. This is a general introduction about Alibaba Dragonwell. which has been open sourced in this year. So what does it mean, a Dragonwell? So the Chinese translation of Dragonwell is Longjing, which is a symbol of Chinese tea culture and happens to be a characteristics of Hangzhou. Hangzhou is a very beautiful city in China where the Alibaba headquarters is located. So, so far for Alibaba Cloud, Alibaba Dragonwell has been default JDK distribution. We just released Alibaba Dragonwell quarterly. We are planning to, release Dragonwell 11 at the end of this year. Okay, I think this is a general introduction about our background, how we use Java inside Alibaba. I think we go to the major part, the technical discussion about these three features. The first feature is elastic heap. So actually, before dive into details about the elastic heap, I just would like to discuss the motivation behind of the elastic heap, why we want to do this. So for this, I just list the two important characteristics of cloud. The first thing is, by using cloud, you can do consolidation. It means you can run multiple workloads in the same physical machine, right? Then different workloads are using CPU memory from the same system. But in another side, most of different workloads are isolated by using virtualizing technology. For example, maybe your application is run on top of virtual machine, right? Maybe run inside of Docker. So this is some background. So if we look at this, if we look at the cloud from resource management point of view, actually you can say, look at the picture, we have two views. So from JVM view, you can say JVM is just managing resources on behalf of user, right? So even, for example, even you don't use memory, and maybe JVM does not have the ability to return unused memory to OS. That's a problem. Another thing is, hypervisor just also is managing resources used by its guest. The problem here is that hypervisor just assumes it has full control of resource management provided by guest. The challenge here is you have two managers, right? We think you don't want two managers tell you different things. So let's talk about the cloud offering model. You can say cloud offering model is a pay-as-you-use model instead of traditional pay-as-you-go model. The problem here is for JVM, the lack of vertical scalability completely prevents the benefits of the pay-as-a-use model. For example, JVM just will force user to over-provision resource. This example, for example, by estimation in extreme case, you need to set up. You need to set maximum heap size when you launch your program. Then in runtime, actually you cannot change the maximum heap size, even if you don't use it, right? So that's a problem. And as I mentioned, the current implementation of OpenJDK does not have the ability to return unused memory to OS. So this is something we call the vertical scalability. I think this is the most important motivation. We want to introduce elastic heap strategy to JVM. I think dynamically adapting JVM resources to better fit your application needs is a very, very important problem. So by using elastic heap, you just can scale memory utilization according to your application needs. This is our purpose. Before I go to the details about the elastic heap, I think I need to go through the basic concepts used by G1. G1 introduced in Java 6 and fully supported in Java 7. So G1 GC is a generational GC, and it just divides the entire heap into the equal-sized region. It has 5 types of heap region. You can just look at the picture. It has, Eden region, survival region, order, humongous, and free. So our elastic heap implementation is based on G1 GC. This is a picture how we can implement elastic heap. For this picture, I just show you how we can return the unused memory to the OS. You can say in step 1, during the stop word phase, in save point, the VM thread will check, do the evaluation. If JVM thinks the 2 heap regions are not used and enough to return OS, then they just put these 2 heap regions into the we called uncommitted queue. This is the first step. In the second step, we will kick off concurrent thread in elastic heap. The concurrent thread will check the uncommitted queue. Then they just call munmap OS API to return the memory into the OS. This is the step 2. So the key point here is our elastic heap are really relying on these 2 API to acquire memory and release memory. I just share some key design points in elastic heap. The key point here is we just offload map and map operation from the VM thread in step 1 to the in stop word time to the concurrent thread in step 2. This is very crucial because map and unmap operation are very, very expensive, and it may cost many CPU cycles. So that's why we want to do it in the concurrent thread, not in the stop word time. So maybe you think the idea is very simple, but not the implementation. So the change here is we need to deal with lots of details. For example, in this case, you need to deal with the synchronization between VM thread and the concurrent thread. So I just go through the details of elastic heap. So what's the use case? What's the user story for elastic heap? This is our real use case used in Alibaba production. You can look at this picture. Actually, in our production, we have 2 kinds of jobs: online job and offline job. Online job is generally written in Java. You can just look at the picture on the bottom. Actually, in this scenario, we have 6 jobs, right? We have 4 online jobs and 2 offline jobs. And the offline jobs is batch-oriented and low priority. But the online job is critical for us. It requires you need to handle request for online job as soon as possible because the response time for online job is very critical. So for this case, in step 1, you can see if we think if our scheduling system found the traffic peak starts, then the scheduling system will kill these 2 offline jobs, then so that the memory could be released into the OS by offline job. After that, then the online job, the JVM for online job, by using is using elastic heap to acquire memory from OS. Then at this time during peak time, the JVM process for online job has enough memory to handle requests. So when the traffic peak ends, then the elastic heap will check again it found the memory are not used because the traffic is down, right? So then it has the ability to return memory back to OS. So when the memory has been released to OS, so the scheduling system in our production will kick off these 2 offline jobs. So, this is a very important thing is, we can, by using Elastic Heap, essentially is a very good way to improve resource efficiency in the cloud. So, this is Elastic Heap, and then we move to the next part about the warm-up. So, what's the warm-up overhead in Java? So the problem is, before reaching to the point of being able to perform useful work, the Java process generally goes through the warm-up phase. So this has been generally understood as a traditional behavior for Java. So let me check. Let me show you what will JVM do during warm-up phase. Actually, there are 3 things will be done in warm-up phase. The first is class loading. So during warm-up, a large number of classes will be loaded from disk by JVM. This is the first thing. The second thing is the classes which have been loaded from disk will lead into the increased number of methods. The message will be called. At the beginning, the message will be executed in interpreter. So you will spend a lot of time in interpreter. This is the second thing. The last thing is even in C1 compiler and in interpreter, the JVM will collect profiling information and do necessary aggressive compilation for your JVM process. So this is the cost of warm-up. This is real case. I just show you the warm-up overhead occurred in our Alibaba production. When the application is kicked off, we have two operations here. The first thing is you will get high CPU consumption. The problem is the compiler thread will use lots of CPU cycles to do the compilation. More worse, the application thread will compete CPU cycles with a compiler thread. This is the first thing. The second thing is the second observation is because most of methods at the beginning are executed in interpreter. So interpreter is kind of very, very slow. So our application might suffer from much longer response time. So during warm-up, in some situation, we saw some lots of timeout issues, timeout problems during warm-up. So generally, a very common practice among application teams that require high performance from start is, to feed your JVM process by using mocking data. Just described in this feature, in this picture. And the bad thing is, even you are using mocking data, the mock data might not cover the real code execution path. That's the problem. If that's problem, the JVM just incorrectly optimize code for your mock data. Then, but later on, sometime later, then your real traffics come in, and the JVM sees something change in execution pattern. Then they just need a bail down and back to the slow interpreter. That's problem. That's the problem caused by mock data. So that's why we want to resolve this. You cannot rely on mock data to resolve a warm-up issue. It's not safe may not produce desired optimization. I also can review the warm-up technologies implemented in JVM context. The first thing is, I think most of you may be familiar with ahead of time compilation, which is an experimental feature introduced since in JDK 9. AOT just sometimes called as a static AOT. Static AOT just takes a collection of classes and just compile all the methods in the classes before running in Java code. This is the first technology to eliminate warm-up overhead. The second category is about cache compilation. So, OpenJ9 just implement a feature called dynamic AOT. Then JVM implement a feature compile stashing. So actually, both of them are very similar. The key implementation here is let's just save compilation results in previous run, then they can reuse the compilation results in next run. Actually, the last category we can use to resolve warm-up cost is we call trace and replay compilation. One feature is called Ready Now, has been implemented by Zen JVM. And in Alibaba Dragonwell, we already implemented J warm-up to resolve and eliminate warm-up cost. This is something we want to discuss more details with you. Okay, I think I just would like to give you the overall process how JVM warm-up work. How does the J warm-up work? Actually, we have two steps in J warm-up. The first step, your application will be deployed into the beta environment. In beta environment, one important thing is, even in beta environment, our application actually receives the real request from the real users. So that's very important, not mock data. So during the phase, then you just send a real request to this JVM instance. In this phase, then the warm-up profile will be recorded as a binary onto disk. After that, in this phase, if our application owner verify everything works as expected, then they can, just deploy the same application version into the production environment. In this phase, then the warm-up profile will be distributed and reused for all subsequent JVM instances. Before traffic come in, the JVM instance can pre-compile the method, the hot methods based on warm-up profile. Then you can just eliminate, by using warm-up, you can just eliminate the warm-up cost in our situation. Okay, so let's talk a little about what's the content of warm-up profile. So majorly, the content of warm-up contains some necessary information which are used for identify which method is hot, which method has been compiled in previous run. So they also contains some information, for example, the method or the class loader, the class information, the class loader, which the method belongs to. So the warm-up profile has been stored in as a binary format on disk. And the current implementation J warm-up, we does not support merge. Maybe we can consider it in the future release. We can, can just merge different profiles for use. You can just look at the picture on your right-hand side. This is the content we have defined for warm-up profile. Okay, this is the key part, I think. JVM just defines these two APIs. These two APIs are very critical. They just give DevOps new control over just-in-time compilation. Then you can choose when you want to do the just-in-time compilation. The first API is we call the notify application startup is done. Then it means when your application startup is done, then your application can call this API to notify JVM your startup is done. Why we need this API? I just would like to share the details in the later by using some concrete example. The second API is you can use this API to check whether or not the compilation is done. If done, then you can just let the traffic come in, right? So I think I can put all of them together, combined with overall process of application deployment. How does it work? So in startup, when the JVM start up, they just pass the warm-up profile. After the pass is done, then the JVM will pre-compile methods if the dependencies are satisfied. This is the first step. Based on our experience, actually most of how the methods would be compiled in this phase. So after that, the application will call this API, notify JVM. Yeah, I'm done. Please trigger eager compilation for me. So the JVM just get notified. Two major things will be done during warm-up. The first thing is the JVM will load and initialize necessary classes in safe way. This load and initialization are done in an eager way. When the necessary classes has been initialized and eagerly, then we can we can trigger the second round of compilation in warm-up phase. So when the step 1 is done and the step 2 is done, then it means almost all your hot methods in previous run has been compiled. So you can just check the warm-up is done, then the application owner the DevOps can just send a request, real request to the this instance, because at this time, this instance is ready to serve the request. So I think this is a hard part. Why we need the first API? Actually, which is pertinent to the class initialization. I just show this the example. This is just to demonstrate the pitfalls in class initialization. So this is the case. We have two classes, right? Full class and the bar class. In step 1, you just create a new instance for full class. Then you call test method on this new instance. After that, you can see full count will get 1, right? It has been increased. In test method, because it calls the static method on bar, eventually it will trigger the initialization of bar class. According to this is just required by JVM specification. So they just trigger initialization of bar. When the initialization is done, then you can see eventually the bar count will get 2, right? This is the normal execution, but if we do it, just compare it, we just do it, initialize the bar eagerly. It means what will happen? It means JVM just call bar CL init directly, but without calling on full test method. So what's the problem? So you just if JVM just initialize bar eagerly, then the results of bar count is 1, right? The problem here is this result is different from the normal execution. That's the problem. So the key conclusion is it's not safe to initialize class eagerly. We need to have some ways. We need to have some other mechanisms to handle this. So that's why we want to come out this API, notify application startup is done. Actually, you can think it's a suggestion by application owner. So when this API is called, then we just have an assumption. It means almost all classes have been initialized by application itself. So it's safe, no worry. After this API is done, then in the second round, we just try best to do the safe initialization for remaining classes eagerly. So you can just look at this picture before API, before this API calling, and the classes has been initialized by application itself. So in this phase, if you have remember in this phase, we just pre-compile methods for all the methods if their dependency has been resolved and been satisfied. After API, then we just eagerly load and initialize class. And then in this phase, if we think the class has been initialized, then we just compile them. So what does it mean, safe initialization? In current implementation, we just think if the initialize of class is empty, it means the user does nothing in class initialization. So it's very safe to just eagerly load this class and do just eagerly initialize that class. Okay, if you remember the chart I showed you in previous slide, this slide just show the orange line is is a warm-up overhead, and represented by base JDK. The blue line is represented by JDK with J warm-up enabled. You can do some simple comparison. Actually, the results is positive. The first thing is you can see peak CPU usage has been reduced from 75 to 56 in our situation. And then you can see the time range in peak has been reduced from 8 seconds to 2 seconds. The worst response time has been reduced from 100 milliseconds to 80 milliseconds. So in order to give you a good understanding about J warm-up, I just give you some comparison between just-in-time and J warm-up. What's the difference between J warm-up and just-in-time? The first thing is I think just-in-time compiler is reactive compilation. The user cannot directly invoke just-in-time compiler, right? But for warm-up, I think it's a proactive compilation. Actually, you can say you can just tell JVM I'm ready. I want to trigger compilation for me. So you can trigger that. The second thing is both of them are very similar. Actually, J warm-up is implemented based on C2 compiler. Both of them need runtime information as inputs. But different thing is for just-in-time compiler, the profiling information has been collected in runtime dynamically, right? But for warm-up, we just get this profiling information from log on disk, right? This is the third thing is for just-in-time compiler. Actually, all the classes are resolved by runtime lazily by your application itself logic, right? But for warm-up, I show you in previous slide, some classes has been resolved eagerly and safely. We just want to compile as many as hot methods after safe initialization. For just-in-time, actually, just-in-time just needs lots of runtime profiles. For example, block profiling, edge profiling, something like. And for current implementation of J warm-up, so far we only record the hot method. This is our current implementation. We just use a warm-up profile to identify which method is hot. Then for our compilation, maybe in the future, we consider, we just consider, take a more profiling information to do compilation so that we can produce a high quality code. So the second comparison between is between relay compiles and JWarmup. Hotspot is a very interesting feature we call replay compiles. What's the difference between replay compiles and warm-up? So the first thing is for replay compiles, it only exists in debugger version, but for warm-up, it has been used in production. They also have a different purpose. For replay compiles, you can just use replay compiles to find the root cause or correct given process in compiled method. But for warm-up, as I have mentioned, yes, we just want to eliminate the warm-up overhead. The last thing is actually both of them are very similar. So for replay compiles, they just repeat the compiling process only for the last compilation task. You can just look at this picture. This is a log generated by replay compiles. They just record the last compilation task. Then they just repeat the compiling process for this last task. But for warm-up, we just record all the hot methods in the previous run. Then we want to compile all of them. Yeah, I think I completed these two parts. The first electric heap, the second is the warm-up. I think we go to the next part about why we want to extend JFR for our needs. Actually, in this part, I would share the two motivations here. How can we resolve excessive GC pause? How can we resolve the excessive de-optimization cost? This is our reason we want to extend JFR to do that. And then the second part is I just go through the implementation details, how we do that. Just to give you a little background, JFR has been open sourced in OpenJDK 11. So we just backport the JFR into Alibaba JDK 8 for internal use. And so far, JFR feature has been included in Alibaba Dragonwell. You can try Alibaba Dragonwell. In the early of this year, we already talked with the community and talk about how can we contribute JFR to the OpenJDK 8. So far, all the patch about JFR has been in incubator branch. I think if you are interested in it, I think you can go to OpenJDK website and try the experimental build for JFR. You can use it for Java 8. So again, we just talk about why we want to do that. The first thing is we just go through the basics of GC performance. So I think the first key fact in terms of GC performance is about frequency. It means how frequent are the GC pause. So how frequent are GC pause you can tolerate. That is the first thing, I think. For GC performance, the second thing is about the duration. So it means how long are those GC pause. So how long our GC pause you can tolerate. So I think this is the two key factors for GC performance tuning. So let's back to the young GC implementation in G1. G1 already use mark and copy algorithms to do the collection for young GC. You can just look at this picture. During marking phase, if G1 found y1, y2, and s1 are live, then all these objects will be copied into the correct destination. So in this case, you can say y1, y2 have been copied into survivor space, and s1 gets promoted to old. So for this, for young GC in G1, actually I have two rule number here. Number one, the frequency of young GC event is controlled by the rate of your application allocation, right? If you have high allocation rate, then you will have very frequent young GC. Also controlled by size of Eden space. If your Eden space is smaller, then you will get a very high frequent young GC. The second thing is the post time of young GC is controlled by live data set, not that, right? In this case, you can see we just copy y1, y2, and s1, and we don't touch any data object. Okay, let's look at this picture. This is our real case. I just gathered from our production. The bottom picture is for CPU consumption, and the top picture is for CPU consumption. The bottom picture is for young GC count. So both of them are from the same application, and you can see along with the time going in x-axis, you can see CPU consumption is almost stable, right? But the problem is the frequency of young GC is turbulent. I just marked in red rectangle. In worst case, you can say the young GC count will happen around 200 times. It's very often. It's frequent. So the problem is how can we resolve it? Can we have some tools to resolve it? Yes, I think maybe you can check the GC log, right? From GC log, actually you can see lots of allocation failures, and you can see many of young GC has been triggered in GC log. The problem here is the GC log cannot tell you what allocate the most objects, right? So that's the problem. That's why we want to extend JFR events to do that. I think this is for excessive GC pause. The second motivation is about excessive de-optimization. Let's go through some basic concepts used by hotspot. Generally, we start off interpreter. Then, when your method gets hot, then we just in time compile it, and in the first level of compiler is C1. So C1 is faster than interpreter, and then if you run a little longer, then we just transition to the C2 compiler, right? So the method will be compiled by C2, and the C2 is very fast than C1 and the interpreter. Actually, during interpreter and the C1, the JVM will collect some profiling information. So the profiling information is something like, for example, if statement is always evaluated as true, then you never run into else block, right? So the non-value never flows into your call site, or you always use array list instead of linked list. This information, profiling information, are useful for C2 compiler. They can use this information to generate more optimized code. The challenge here is if you have something changed, for example, if the speculation fails, the challenge here is the JVM must bail back to the interpreter. It's very slow. So this is sorry. Hmm? Huh? Any other? Uh, Sorry. Um, okay, I think yeah. So something wrong, I think. Okay. I think I can go. Yeah, we talk about the de-optimization. De-optimization is cost, right? So let's talk about our implementation. So before talking about our implementation, let's talk about the current implementation of Java. Which kind of event the current implementation of Java has support? This is you can just look at the picture. In current Java implementation, they just support two kinds of event. The first is event object allocation outside TLab. The second is in new TLab. I just show the example here. You can look at this picture. We have three rows in this picture. Each row represents a different thread, right? So for this table, you can see how many allocation happened in TLab and how many allocation happened outside TLab. Actually, this information is quite useful for developers. For example, if the significant allocation happened outside TLab, I think you have two choices to optimize your application. The first thing is maybe you choose to optimize your object and reduce the size of object being allocated. Or you can adjust the TLab size and increase it. And because at this moment, you just get a performance penalty on TLab allocation. So this is our JVM parameters we used. The first is enable GFR. By using it, we can enable GFR features for Alibaba JDK. The second thing is we just provide two options for our implementation. The first is sample object allocation. The value is true or false. If it is true, it means you want to do object you want to sample object allocation. And the second thing is you can configure the interval. So for example, if you set your object sampling interval as 10, it means you will take samples, object allocation samples at the first, the 11th, the 21st, and the 31st, and so on. So this slide just shows when we do the sampling allocation. You can just look at this picture. Here is some basic concept used in hotspot. Object allocation always happens in Eden space, and TLab has been used by hotspot for fast allocation. In this example, we have two threads, T1 and T2. Each of them have their own TLab space. So when we do object allocation sampling, the first place is when the object has been allocated from TLab. When the allocation is done, then we can trigger the sample. Otherwise, if for example, the TLab is not enough, and then go to the slow path, then we can just even in slow path, we also track and want to take samples for your object allocation. So this is implementation. How we implement object allocation samples. Actually, this is a piece of pseudocode. I just show the skeleton of our implementation. Majorly, we have three steps. In the first step, we just check whether or not the sampling flag is enabled. Actually, we just check this option. sample object allocation. In step 2, we just check whether or not the current allocation is a sampling target. If you remember, this target actually has been controlled and configured by object allocation sampling interval. If the condition in step 1 and step 2 are satisfied, then we can do sampling and file-related GFR event. This is our assembly code. Is dumped by turning on print compilation JVM parameter. So this is trace event XML file. This file is a place where the JAlpha events were declared. And yeah, maybe you can say we add 2 events in this XML file. So the first event is we called up to instance object allocation. This event for instance object allocation. The second event is we called array object allocation, is for array. So what's the up to? Up to is a prefix. It's a terminology used in hotspot in OpenJDK. It means we just only generate samples in C2 compile code. So far, our implementation does not support C1, does not support interpreter. Yeah, last thing is actually you can browse these 2 events in the Java mission control. You can see this picture. You can open the Java mission control, and these 2 events will be displayed if you have generated them. So let's talk about why we have 2 events for array and for instance. The consideration is about footprint. We want to save footprint for events. Our optimization is based on the 2 facts. The first fact is the size, length of array cannot be determined statically. So we need a record array size for every sample. But for instance object, it's different because the size of instance can be deduced from class type. So if and only if all the instance object allocation events belong to the same class type, then we can just record the object size in the class constants of JAlpha binary. So the key consideration here is we no need to record the object size for every instance object event. Yeah, this is some disadvantage of our approach. You can see we just take samples at a fixed rate, right? For example, if I just set interval as a 2, then I just take a sample at the first, at the third, and at the fifth. Then if we just take this example, the large array will be allocated at the even number of times. So this large array allocation will be missed in our approach. So in our future work, we may consider introduce some statistical distribution, for example, Poisson distribution, to generate more random samples for our approach. Yeah, the array will be missed. So far we already have the GFR events, right? So the next question is, how can we display results to our developers? How can easily tell our developers which method has consumed much more memory, allocate much more objects? In our situation, we just want to use flame graph to tell which method is hot for memory consumption. Actually, I think most of you may be familiar with, you can use a flame graph to tell which method for CPU consumption, right? In our case, actually, we also can use a flame graph in memory allocation for object allocation. So we just create a tool we call the JMCX. Then you can use this tool to convert the GFR events to flame graph. So this is sample overhead. Maybe you are wondering what's the impact introduced by a solution. The first observation is if the flag allocation is false, actually the sampling code even does not generate by C2 compiler at the compile time. So nothing impact on your real workload. But if the flag is true, it means if you very lower interval, sampling interval, then maybe you will suffer from higher performance overhead. So this is the frame graph. I just show the results. This is our real case. You can see in purple part, most objects are allocated in purple part. So you can tell you which method has allocate the objects. So if you can use this information and optimize your code, then you can just do some optimization for purple part. Then the object can be gone. Then the young GC frequency can be reduced. So I think this is last part, and I think time is up. Maybe I think I can quickly go through the last part for we call the FDO. Actually, FDO technology exists for traditional compiler. You can use FDO to generate more optimized code. Actually, we also can do the similar things for JVM. In our situation, in step 1, actually you can record the compilation results into as a GFR event, and in step 2, you can also use JMCX to create compilation policy from the GFR events, and the next run you can you can just enable just use the FDO information to your next run. This is the compilation policy file we used. In this file, you can see this has been constructed as a hierarchical structure. It contains which class loader, which class entry, and which method has been de-optimized. And then it also records the de-optimized region. So by using FDO compilation policy, you can see this is results. Normal baseline, the blue line is normal Z compilation. The orange line is with FDO enable. By FDO enable, you can see we can reduce CPU usage. Yeah, I think this summary. I think in my talk, I majorly covered 3 major features. The first is elastic heap. The second is warm-up. And I think so far the current release of Dragonwell does not include our extension for GFR. But we are planning to make it to the next release of Java Dragonwell in the end of this year. And thanks, many thanks for your attention. And that's all.